A speck of dust in your hand contains the atoms of a star that died before Earth was born. This is the reality of intergalactic dust, the silent carrier of stellar DNA. By the end of this journey, you will see the night sky not as distant lights, but as your extended home. How did the violent death of a star forge the very materials that built our world? And what cosmic messages are written in this ancient dust? What does it mean to know you are made of star stuff deep within a nebula's glowing clouds? A new star flares to life. This is not merely a light being switched on in the void. It is the ignition of a titanic engine, a cosmic factory whose sole purpose is transformation. At its unimaginably hot core, the simplest building block of the cosmos, hydrogen, is squeezed together under immense pressure. This process, nuclear fusion, forces hydrogen atoms to merge, creating a new element, helium, and releasing the torrent of energy that makes the star shine. For billions of years, this factory hums along, but its work is only beginning. In the most massive stars, this creation does not stop. As hydrogen fuel dwindles, the core contracts, growing even hotter. Now the star begins fusing helium atoms into carbon. Then carbon atoms are forged into oxygen, and so the chain continues, building ever heavier elements layer by layer like the rings of a tree. In a final, furious burst of activity, a star can create silicon, and then, at the very end of its life, iron. This stellar alchemy is the universe's primary source for nearly every substance we know. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all of it was cooked in the heart of a star that lived and died long ago. The brilliant life of a star is a story of creation, but it is a story with a violent, necessary ending. For these newly forged materials to escape their stellar forge, the factory itself must be torn apart. Iron is the star's final and most treacherous creation. Unlike all the elements that came before it, fusing iron does not release energy, it consumes it. In that instant, the star's central engine sputters and dies. The outward push of radiation that has supported the star against its own immense gravity for millions of years vanishes. Catastrophic collapse is now inevitable. The core, which may be larger than our entire Earth, crushes down upon itself in a fraction of a second. This implosion triggers a titanic rebound, a shock wave of unimaginable force that rips the entire star apart from the inside out. This is a supernova. For a few glorious weeks, this single exploding star can radiate more light than every other star in its galaxy combined. But the true purpose of this cosmic detonation is not the light show. It is the scattering. The supernova's blast wave hurls the star's own carcass, a cloud now saturated with newly forged carbon, oxygen, silicon, and iron, out into the void at millions of kilometers per hour. In that single, spectacularly violent act, the star dies, but its elemental essence, its very DNA, is liberated. This enriched material, a turbulent mix of gas and the first specks of freshly minted dust, becomes the raw feedstock for everything to come. Within the cooling chaos of the supernova's expanding remains, a quiet miracle begins. The temperature plummets from millions of degrees to a mere few hundred, a shift so extreme it fundamentally changes the nature of the stellar debris. Atoms of silicon, carbon, and iron, once racing apart at incredible speeds, now slow down enough to meet and connect. They begin to stick together in a delicate cosmic dance known as nucleation. This is the universe's ultimate recycling process in action. Picture how, on a cold winter day, invisible water vapor in our own air coalesces around a tiny speck to form a unique, intricate snowflake. A similar process unfolds here, but instead of water, the building blocks are the very elements forged in the star's final moments. Each collision, each new bond, creates a microscopic solid particle. These are the first true grains of stardust. Some may have a crystalline structure, an orderly atomic arrangement, while others are amorphous, a more chaotic jumble of atoms. Each grain is a unique capsule, a tiny safe containing a specific mix of the star's elemental legacy. This condensation is an incredibly fragile process. It depends entirely on the precise conditions within the supernova's ejector, the exact pressure and chemical composition of the expanding cloud. If things are too hot or too turbulent, the grains cannot form. But when the conditions are just right, the gaseous remains of the star complete their final transformation, becoming solid matter. This is the pivotal moment the star's liberated DNA is packaged for delivery, transformed from a diffuse cloud into resilient, tangible particles ready to endure an epic voyage across the galaxy. These newly formed dust grains are far more than simple specks of cosmic dirt. Each one is a complex mineralogical specimen, a microscopic time capsule sealed with a unique chemical signature. To understand what they are, scientists use a powerful technique called spectroscopy. This method analyzes the specific wavelengths of light a grain absorbs or emits, revealing its elemental composition with incredible precision. It is like listening to the grain's own faint song, a song that tells us exactly what it is made of. We discover there are families of stardust. Some are silicate grains, rich in silicon and oxygen, the fundamental ingredients of rock and sand. Others are carbonaceous grains, built primarily from carbon atoms arranged in structures that might resemble the graphite in your pencil or the diamond in a ring. Then there are the truly exotic Presolar grains, tiny diamonds and other rare materials that formed in other stellar environments long before our own sun ignited. The most revealing detail, however, is not just which elements are present, but their specific isotopic fingerprints. Isotopes are different versions of the same element, atoms that have the same number of protons but a different number of neutrons in their core. The precise mix of these isotopes within a single dust grain acts as a unique barcode. For example, a specific ratio of neon or xenon isotopes is a telltale sign, a chemical signature that can only be forged in the heart of a supernova. This detailed composition is the literal DNA of the dead star, a complex chemical code that tells us not only what the star was made of, but how it lived and how it died. Propelled by the supernova's fury, these newly formed dust grains are flung into an immense and alien ocean. This is the interstellar medium, the space between the stars. Do not picture a perfect, empty void. It is a diffuse sea of tenuous hydrogen and helium gas, crisscrossed by invisible currents of radiation and dotted with other, older grains of cosmic dust. For a microscopic speck, this journey is anything but a calm drift. The gentle but constant push of starlight, a force called radiation pressure, acts like a cosmic wind, billowing against the dust and slowly guiding its path. Simultaneously, the faint gravitational tug from distant stars and nebulae pulls it along invisible highways. This voyage is fraught with existential danger. High-energy cosmic rays, atomic nuclei racing across the galaxy at nearly the speed of light, can blast individual atoms right off a grain's surface, slowly eroding it over eons. Even more destructive are the shock waves from other, nearby stellar explosions. These titanic pressure fronts can slam into a dust grain with the force of a supernova, either vaporizing it instantly or shattering it into a cloud of even finer fragments. It is a testament to the resilience of this stardust that so many of these tiny capsules survive. They endure this chaotic, million-year pilgrimage to join a grand cosmic reservoir, a swirling mist of ancient materials adrift between the stars. This ejection is merely the first, perilous step in an epic voyage that will carry the star's legacy across unimaginable distances. This journey through the interstellar void would seem to guarantee destruction, yet Stardust is engineered for survival. These are not simple, brittle specks. Many possess complex, onion-like layered structures where a core of one mineral is carefully sheathed in another, creating a microscopic fortress that can absorb impacts and resist erosion. Even more remarkable is their attire. Drifting through the coldest molecular clouds, a dust grain can accumulate a thick, icy mantle of frozen water, ammonia, and methane. This frosty coat is not just decoration, it acts as a sacrificial shield. When a damaging cosmic ray strikes, it is this icy layer that takes the hit, vaporizing to protect the precious stellar information locked within the grain's mineral heart. Some of these travelers are even magnetized, carrying a faint magnetic field from their fiery birth. This allows them to sense and align with the faint magnetic currents that weave through our galaxy, like a microscopic compass needle. This alignment might gently guide their long-term motion, helping them navigate the galactic sea and even lending their structure a bit of extra stability against the chaos. A grain's ultimate fate is a cosmic lottery dictated by its size, its exact chemical makeup, and the sheer luck of its path. The smallest grains are quickly destroyed, while the largest and most robust endure. Those that survive are the veterans of deep space. They are the ancient ones, having drifted for billions of years, silently witnessing the birth and death of countless stars. This incredible resilience transforms them from simple debris into the most reliable historians of our galaxy, their durable forms carrying an unaltered record from a time long before our sun was even a glimmer in a nebula. Yet for a select few grains of stardust, even the vast expanse of a single galaxy is not the final frontier. These Voyagers are destined for an even more profound journey, one that carries them across the cosmic divide between galaxies. This incredible ejection is made possible by the most violent and energetic events in the universe. The collective fury of countless supernovae in a galaxy can generate immense galactic winds, powerful outflows that sweep up gas and dust and hurl them clear out of the galactic disk. Even more potent are the forces unleashed by supermassive black holes at a galaxy's heart. As these monsters feed, they can blast out titanic jets of energy, creating pressure waves that can literally blow the raw materials of stars right out into the emptiness beyond. This is how a dust grain forged in the death of one star finds itself cast adrift from its entire home galaxy. It now enters the intergalactic medium, a realm of near nothingness. The space between galaxies is not just empty, it is profoundly, almost perfectly void. The density here is 1,000,000 times lower than even the thin interstellar sea within a galaxy. For a dust grain, this is a voyage through near total darkness and silence, a journey measured in billions of years. There are no gentle stellar winds here, no glowing nebulae to pass by. Its only companions are the faint, cold glow of the cosmic microwave background radiation and the imperceptible tug of gravity from structures too distant to see. A grain might drift for eons, a solitary speck in an infinite black ocean, its journey seemingly without end. But this isolation is not necessarily permanent. The same force that guides the planet's gravity can still reach across the void, a passing galaxy, or even a large, diffuse cloud of dark matter. can exert a gravitational pull, slowly bending the dust grain's path over astronomical timescales. It might be captured, spiraling slowly into a new, foreign galaxy to join its reservoir of cosmic ingredients. Alternatively, if its velocity is just right, it could continue its solitary drift forever, a permanent wanderer in the intergalactic darkness. The confirmed discovery of dust floating in these immense voids was a revelation for astronomers. It proves definitively that the elements forged in stellar hearts are a universal resource. They are not locked away in their home systems or even their home galaxies. They are a shared inheritance capable of traveling the entire cosmic web. This is the ultimate dispersal of a star's legacy. The iron from that long-dead star's final moments, the carbon from its earlier life, the oxygen that fueled its brilliance, all of it can be cast across the universe. One of these intergalactic voyagers, after a journey of billions of years, could have been the very seed that helped form our own solar system. The fact that you are listening to this story, built from atoms that crossed such an unimaginable gulf, means that the story of Stardust is not just a history of our galaxy. It is a history of the entire cosmos, written in the dust that dances between the stars. This unaltered snapshot is the closest we can ever get to time travel. The precise ratios of elements within a single grain, its isotopic signature, remain frozen in time from the very instant the star died. This is a direct physical sample of that final, cataclysmic event, giving us a laboratory specimen of processes that occur at temperatures and pressures we could never hope to recreate on Earth. To hold such a grain is to hold a piece of a star's last will and testament. Scientists retrieve these cosmic time capsules in two primary ways: specially designed spacecraft, equipped with collectors made of a substance called aerogel, can gently catch pristine dust particles as they drift through our solar system. Even more remarkably, we find them right here on our own planet. Certain ancient meteorites, which have fallen to Earth after traveling the solar system for billions of years, are found to contain tiny, resilient presolar grains embedded within them. These grains predate our own sun. They are literal survivors from other stellar systems, and by analyzing them with incredibly sensitive instruments, researchers can perform a kind of cosmic forensics. They can measure the grain's age and, by reading its unique isotopic barcode, identify the exact type of star that gave it life. Was it a red giant, a supernova, or perhaps a more exotic stellar object? The dust holds the answer, preserving a stellar identity that would have otherwise been lost to the void. This is why Stardust is so much more than cosmic debris. It is the ultimate witness, a silent historian that has carried the unvarnished truth across the expanse of deep time. The faint whisper of stardust can be heard by listening to the light of distant suns. When starlight travels across the galaxy, it passes through immense clouds of this cosmic dust. The dust does not block the light completely. Instead, specific minerals within the grains absorb very particular colors or wavelengths of that light. Powerful telescopes, especially those equipped with infrared eyes, can detect these unique absorption signatures. It is like analyzing a fingerprint left on a beam of starlight, revealing the exact chemical makeup of the dust cloud it traveled through. This method allows us to map the distribution and composition of this stellar residue across the galaxy, all from a staggering distance. But to truly understand a star's legacy, we needed to bring a piece of it home. This was the daring goal of missions like NASA's Stardust spacecraft. It flew into the tail of a comet, a cosmic freezer preserving ancient material, and deployed a collector made of aerogel. This substance is a ghostly solid, a foam so ethereal it is 99% air. When a microscopic dust particle moving at incredible speed strikes the aerogel, it is gently caught and slows down without vaporizing, leaving a tiny, carrot-shaped track in the material for scientists to recover. Among the captured particles were confirmed grains of interstellar dust, actual physical samples gathered from the void between the stars. Yet the most accessible source of this ancient material is not in space, but all around us, falling from the sky. Certain primitive meteorites, time capsules from the solar system's birth, are treasure troves of presolar grains. These microscopic diamonds and silicon carbide bits are older than our sun itself. Finding them is an epic search on a miniature scale. Scientists begin by crushing a small piece of the meteorite into a fine powder. They then dissolve this powder in a series of strong acids, a process that meticulously eats away all the material that formed in our own solar system. What remains, a tiny residue representing less than 1/100% of the original sample, is a collection of the most resilient presolar grains. The final identification relies on their most telling feature, their exotic isotopic signatures. The ratios of different forms of elements in these grains are wildly different from anything found in our solar system. A grain with a specific, rare mix of neon isotopes, for example, could only have been forged in the heart of a particular type of supernova. This is the ultimate confirmation. It means we are not just theorizing about stardust. We can literally hold in our hands a microscopic piece of a star that died billions of years ago, a tangible piece of our own cosmic ancestry. The microscopic grain, now isolated from its meteorite prison, holds its secrets tight. Unlocking them requires tools of almost unimaginable precision. In specialized laboratories, scientists become cosmic cryptographers, deciphering the atomic language written within. One of the most powerful techniques is called secondary ion mass spectrometry. Here is how it works. A focused beam of ions, essentially charged atoms, is aimed at the grain's surface. This beam gently sputters the sample, vaporizing atoms from its outermost layers. These liberated atoms are then ionized and propelled into a mass spectrometer, a device that acts as a cosmic scale. It separates these ions solely by their mass, measuring the exact weight of each atomic fragment with incredible accuracy. This process reveals the grain's precise elemental and isotopic composition. It is the equivalent of listening to the grain's unique atomic song and writing down every single note. The data tells us not just what the grain is made of, but the exact recipe, including the rare isotopic spices that point directly to its stellar origin. For a view of the grain's physical architecture, researchers turn to transmission electron microscopy. This method is nothing short of looking into the heart of the matter. A beam of electrons is fired through an ultra-thin slice of the dust grain. As the electrons pass through, they interact with the atoms inside, creating a shadow image that can be magnified millions of times. The result is a direct picture of the grain's crystal structure. Scientists can see the orderly rows of atoms, the boundaries between different mineral phases, and any internal layering that formed during the grain's violent birth in a stellar explosion. It is like being able to read the grain's personal diary, page by page, seeing the conditions it endured written in the very arrangement of its atoms. The scale of this work is almost beyond comprehension. These analyses are performed on samples that are often only a few micrometers in size, far smaller than the width of a single human hair. Manipulating such a tiny object requires steady hands, robotic precision, and an immense amount of patience. One wrong move, and a billion-year-old time capsule could be lost forever. But the reward for this care is a definitive answer. The data allows researchers to perform a kind of stellar genealogy. They can distinguish between a grain born in the relatively gentle, outflowing winds of an aging red giant star, and one forged in the unimaginable violence of a supernova. A specific overabundance of certain oxygen isotopes points to one type of star, while a strange mix of calcium and titanium isotopes screams of another. This detailed analysis is the final step in the long journey of discovery. It is how we finally translate the chemical code, reading the entire life story of a star from the silent, atomic testimony of a single speck of dust. These ancient dust grains, survivors of a journey across the galaxy, finally find their calling. They are no longer mere cosmic flotsam. When a vast cloud of gas and dust begins to collapse under its own gravity, spiraling in to birth a new star, these particles become the fundamental seeds of worlds. The process is called accretion, and it begins with a gentle, almost imperceptible touch. As the cloud swirls, individual dust grains bump into one another. Thanks to weak electrostatic forces, they do not bounce apart. They cling together, a microscopic handshake that forms the first fragile bonds. This is how the universe builds from the ground up. A single grain becomes a cluster. Clusters collide and merge, growing into pebbles. Over thousands of years, pebbles accumulate into boulders, and boulders slam together to form mountain-sized bodies called planetesimals. This is not a gentle dance. It is a chaotic, violent construction site on a cosmic scale, a relentless series of collisions and mergers. The heavy elements locked within the stardust, the legacy of those stellar deaths, are the very materials that give these growing bodies their substance. The iron from a supernova's final heartbeat becomes the core of a new world. The silicon and oxygen from a red giant's outer layers form the mantle and the crust. The carbon and nitrogen become the bedrock for complex chemistry. This is the ultimate fate of that liberated stellar DNA. It does not simply drift forever. It becomes the rock, the metal, and the air of new planets. Our own Earth is a monumental collection of this stardust, a planet built almost entirely from the ashes of dead stars. Every mountain, every ocean, every breath of air contains atoms that were forged in stellar furnaces that shone billions of years ago. The ground beneath your feet is quite literally made from the remnants of cosmic giants. This profound connection transforms the story of the universe from one of isolated events into a continuous cycle of death and rebirth. The cataclysmic end of one star is not a finale. It is the essential first step in the creation of a new world, a new chance for Stardust to coalesce into something more. But the story of Stardust does not end with the formation of rocks and planets. This ancient material carried something far more precious within its microscopic structure, the very seeds of life itself. We find stunning evidence for this in a special class of space rocks known as carbonaceous chondrite meteorites. These are not just any asteroids, they are cosmic time capsules that have remained virtually unchanged since the solar system's birth, and they are incredibly rich in presolar stardust. When scientists analyze these primitive stones, they make a breathtaking discovery. Locked within their matrix are amino acids, the fundamental building blocks of proteins and other complex organic molecules. This tells us that stardust is more than an inert mineral. It can act as a tiny chemical laboratory. Drifting through the cold molecular clouds of space, a dust grain's icy mantle provides a sheltered surface where simple atoms and molecules can meet, link together, and form increasingly complex organic compounds, shielded from harsh radiation. This is probiotic chemistry in its most nascent form, occurring on a cosmic scale. Then, during the early solar system's violent period of heavy bombardment, trillions of such dust-rich meteorites and comets pummeled the young Earth. They delivered their cargo of organic, rich stardust directly to our planet's surface, seeding our world with these essential compounds. Every critical element for life as we know it has a stellar origin. The phosphorus that forms the backbone of our DNA, the iron that carries oxygen in our blood, the calcium that strengthens our bones, all of it was forged in stellar explosions and delivered by this cosmic dust. This transforms our understanding of stardust. It is not merely a geological building block, it is a biological one, the chemistry that allows you to exist, to think, and to wonder about the stars is written directly in the atomic code of those long-dead suns. The dust settling on your bookshelf has a cosmic cousin, but the two could not be more different. Household dust is a chaotic mix of skin cells, fabric fibers, and soil. Cosmic dust, however, is a collection of meticulously engineered mineral grains, each with a specific crystalline structure and a unique chemical history. To think of them as simple dirt is to mistake a library for a pile of scrap paper. Another persistent myth paints this dust as the astronomer's nemesis, an annoying cosmic fog that blurs our view of distant stars. It is true that dust clouds can block visible light, but they are far from a mere obstacle. When we turn our telescopes to the infrared part of the spectrum, these same clouds begin to glow with their own light. They become brilliant beacons, revealing their chemical composition and temperature. Far from hiding the universe's secrets, dust clouds are the very medium in which those secrets are written. We are not just looking past the dust, we are actively reading it, and this readable material is anything but rare. Stardust is the most common solid substance in the entire universe. It drifts in the vast expanses between stars, it floats in the immense voids between galaxies, and it was the primary ingredient from which every planet in our solar system coalesced. It is more ubiquitous than the hydrogen gas from which stars are born. The next time you feel a sense of empty space between the stars, remember it is actually a sea of countless microscopic worlds. Each of these grains is a complex individual. They are not identical specks of cosmic soot. Under an electron microscope, we see their incredible diversity. Some possess layered shells like microscopic onions, built up over eons in the stellar winds of aging giants. Others are tiny diamonds forged in the shockwaves of supernova. Their surfaces are often coated in icy mantles of frozen water and organic molecules, turning them into tiny, flying chemical laboratories. This intricate architecture means every grain has a different story to tell, a different chapter in the epic of stellar life and death. All of this dismantles the final and most profound misconception, the idea that we are merely inhabitants of the Earth, separate from the cosmos above. The iron in your blood that carries oxygen, the calcium in your bones that gives you structure, and the carbon that forms the foundation of your very DNA, all of these atoms were once part of this swirling cosmic dust. You are not just looking at the stars, you are a collection of their recycled essence. Understanding the true nature of stardust transforms it from a distant curiosity into a mirror, reflecting our own ancient and spectacular origins. This constant churn of creation and destruction means our galaxy is breathing. It inhales pristine hydrogen gas and exhales a chemically enriched wind, a cycle that transforms the entire galactic ecosystem over billions of years. This grand process, often called the Baryon cycle, turns every galaxy into a dynamic engine of cosmic renewal. At the heart of this engine is a powerful force known as stellar feedback. This is not a gentle suggestion, it is the collective roar of stars shaping their own environment. The fierce winds blowing from massive, young stars and the titanic shockwaves from supernova act like a cosmic piston. They pump enormous energy and momentum back into the surrounding gas and dust, violently pushing material out of the galaxy's star-forming disk. Some of this ejected matter, a fog of gas and dust grains, is flung so forcefully it escapes the galaxy's gravitational pull entirely, becoming a permanent part of the intergalactic wilderness. But a significant portion of this enriched material does not escape forever. It rises high above the galactic plane in vast, hot fountains, only to cool over millions of years and fall back down like a gentle cosmic rain. This returning shower is not the same pristine hydrogen that began the cycle. It is now heavily laced with the legacy of dead stars, a rich soup of oxygen, carbon, iron, and silicon, all packaged within resilient dust grains. This is the universe's ultimate recycling program. Each new generation of stars forms from gas and dust that has been through this process before. The very first stars in the cosmos, known as population 3 stars, were colossal giants made only of hydrogen and helium. They lived fast, died young in spectacular supernova, and seeded the void with the first heavy elements. The next generation of stars formed from this slightly enriched material, and their deaths added even more complexity to the cosmic reservoir. Our own Sun is a 3rd or 4th generation star. This means the dust that coalesced to form our Earth and everything on it had already been processed through the life and death of multiple ancient suns. The calcium in your bones and the iron in your blood are not just stardust, they are recycled stardust, their atoms having witnessed the birth and death of stellar generations long since vanished. This gradual enrichment is why the universe grows more chemically complex over time. It is a story written in the rising abundance of heavy elements, a narrative of cosmic evolution where the dust itself is both the author and the ink. So the dust that once blinded our view now becomes our greatest source of illumination. This is the power of infrared astronomy. While our eyes see only darkness where a dust cloud blocks the stars, an infrared telescope perceives a radiant glow. The physics is simple yet profound. A tiny dust grain absorbs the energetic light from a nearby star, heats up by a few degrees, and then re-emits that energy not as visible light, but as a warm infrared signature. It transforms an opaque cosmic curtain into a brilliant, shining screen. This fundamental shift in perception is why telescopes like the James Webb Space Telescope are genuine time machines. They are engineered to see this specific infrared glow, to peer directly into the heart of the dusty nebulae where visible light telescopes see only a blank black void. Within those glowing clouds, we witness the universe's most sacred act, the birth of new solar systems. We see young stars, their fiery cores freshly ignited, still swaddled in thick, swirling cocoons of gas and dust. And within those cocoons, we can discern the faint, warm rings of protoplanetary disks, the actual nurseries where dust grains are colliding and coalescing right now to form new worlds. This is not just observation, it is witnessing creation in real time. The dust that once hid these processes now, under the infrared gaze, actively reveals them. It shows us the temperature of a stellar nursery, the density of a planet-forming disk, and even the chemical composition of the raw materials. By reading the specific infrared fingerprint of the light, astronomers can determine if the dust is rich in silicates or carbon, mapping out the mineralogical diversity of a star system in its infancy. This capability lets us trace the entire life cycle of cosmic matter. We can watch as a supernova's ejector, a cloud of gas and newly forged elements, begins to cool and condense into the first solid dust grains. We can then follow those grains as they are swept up by galactic winds, eventually becoming part of a new molecular cloud where the cycle begins again. The infrared universe shows us the hidden architecture of existence, the dusty skeleton upon which galaxies are built and evolve. Without this view, we would be missing half the story, the solid, tangible half that builds planets and seeds life itself. Our own sun holds a future written in stardust. While it will never face the cataclysmic supernova death of its more massive cousins, its end will be no less significant to the cosmic cycle. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core. It will then swell into a magnificent red giant, its outer atmosphere expanding to engulf the orbits of Mercury, Venus, and likely even Earth. But this expansion is not a violent explosion. It is a gentle, relentless unfurling. For eons, the Sun will pulse, its outer layers becoming loosely bound and turbulent. Then, in a final act of stellar rejuvenation, it will eject these layers entirely, casting them off into space in a series of powerful, gentle winds. This expelled shell of gas, illuminated by the Sun's hot, exposed core, will blossom into one of the universe's most beautiful structures, a planetary nebula. Within this glowing cloud of solar material, a quiet miracle will occur. The temperature will plummet, allowing atoms of carbon and other elements forged in the Sun's final millennia to slow down and find one another. They will begin to stick together, nucleating into solid particles. This is the moment our Sun completes its own contribution to the galactic supply chain, transforming a portion of its being into a new generation of cosmic dust, grains enriched with the unique chemical signature of its long life. This dust, along with the vast cloud of gas, will be pushed outward by the pressure of starlight from the dying core, eventually escaping the nebula to join the interstellar medium. There it will drift for millions of years, slowly mixing with other debris from long-dead stars. It might be swept up by the gravitational pull of a passing molecular cloud, a vast, dark nursery for new suns. Within that cloud, our Sun's legacy would mingle with the dust of ancient supernova, becoming part of the raw material for a future star system. A planet forming in that distant system could quite literally be built from the ashes of our Sun, its rocks and atmosphere carrying atoms that once warmed our world. Perhaps on that future world, the carbon from our Sun's final breath could become a building block for chemistry we cannot even conceive. This is the profound role of every star, large or small. The universe does not waste a single atom. The gentle death of a star like our Sun is just as crucial as the violent end of a giant, a quiet but essential verse in the epic poem of cosmic rebirth. The story of Stardust is written across the entire cosmos, not just our own galactic neighborhood. When we peer into the depths of space, we find that dust tells a different tale in every type of galaxy it inhabits. Take our own Milky Way, a majestic spiral galaxy. Its elegant arms are not just patterns of light, they are bustling cosmic factories. These spiral arms are rich with dense molecular clouds and vast reservoirs of dust, the essential fuel for birthing new generations of stars. The dust here is active and plentiful, constantly being produced and consumed in the ongoing cycle of stellar life and death. But travel to a giant elliptical galaxy, and the scene is profoundly different. These vast, egg-shaped collections of ancient stars appear smooth and featureless. They are cosmic retirement homes, galaxies where the frenzy of star formation has largely ceased. Most of their gas and dust has already been used up, either forged into stars long ago or violently expelled by supermassive black holes at their centers. The little dust that remains is old and quiet, a relic of a more active past. Then there are the starburst galaxies, the cosmic equivalent of a raging wildfire. In these frenetic environments, stars are forming at a rate hundreds of times faster than in our own Milky Way. This explosive birth rate generates immense amounts of dust, but it also creates a paradoxical problem. The very dust that is being produced enshrouds the entire galaxy in a thick, opaque cloak. This dust is so dense that it absorbs the visible light from billions of brilliant young stars, hiding the very spectacle it helps create. To see the furious activity inside, astronomers must look with infrared eyes, perceiving the heat glow from the dust itself rather than the hidden starlight. This incredible diversity is not just a curiosity, it is a powerful diagnostic tool. By simply measuring the amount and type of dust in a distant galaxy, astronomers can read its life story. A dusty spiral is in its prime, actively building. A dust-poor elliptical is in its golden years, its major construction projects complete. A shrouded starburst is experiencing a dramatic, perhaps short-lived growth spurt. This means that a single speck of dust is more than a relic of a dead star. It is a pixel in a much larger picture. Its presence or absence connects the small-scale physics of stellar death directly to the grand, billion-year narrative of how entire galaxies live, evolve, and change their character over cosmic time. This very dust that carries the secrets of the stars also draws a veil across the cosmos. Dense clouds of intergalactic dust act like a cosmic fog, absorbing and scattering the light from everything that lies behind them. A brilliant star cluster, a glowing nebula, an entire galaxy, all can be rendered invisible to our optical telescopes by a thick, intervening wall of this material. Astronomers call this effect extinction, and it has been one of the most formidable obstacles in mapping the universe. For centuries, the true center of our own Milky Way remained a mystery, completely hidden from view by the sheer density of dust clouds along our line of sight. We knew something immense was there, a gravitational anchor for our entire galaxy, but its nature was a total blank, a great unknown painted in darkness. To pierce this veil, science had to learn to see in new ways. We turned our instruments to the radio and infrared parts of the spectrum. These longer wavelengths are far less affected by dust, slipping between the tiny grains like sound passing through a wall. Radio waves can travel unscathed through clouds that would block visible light entirely, while infrared light is actually emitted by the warm dust itself, turning the obscuring curtain into a radiant map. This is not merely a workaround, it is a fundamental shift in perception. By listening to the radio whispers and reading the infrared glow, we have finally unveiled the galactic center, discovering the supermassive black hole that resides there. Correcting for this obscuration is now a cornerstone of modern astronomy. Every observation of a distant object must be carefully analyzed to account for how much its light has been dimmed and reddened by the dust in its path. Without this crucial correction, we would be measuring a universe that is dimmer, smaller, and fundamentally distorted. This is the profound duality of cosmic dust. It is both the brilliant author of stellar history and the keeper of cosmic secrets, a substance that reveals as much by what it hides as by what it carries. Deep within the vast population of cosmic dust, scientists sometimes uncover true outliers. These are grains with such strange and unexpected isotopic signatures that they stand completely apart from the rest. They are the cosmic equivalent of finding a sentence in an ancient language that no one has ever seen before. These anomalies are not mistakes in the data, they are profound puzzles, each one pointing a finger at a rare and extreme stellar event that our standard models struggle to explain. One of the most thrilling possibilities is that some of these anomalous grains were forged not in a supernova, but in an event of even greater violence and rarity, a neutron-star merger. When two of these incredibly dense stellar corpses spiral into each other and collide, they unleash a cataclysm that ripples spacetime itself. In the fiery aftermath, conditions become perfect for rapid neutron capture, a process that seeds the surrounding space with a rich cocktail of the heaviest elements, including gold, platinum, and uranium. A dust grain carrying the distinct isotopic fingerprint of this event would be a smoking gun, a direct physical sample confirming that these cosmic collisions are indeed the universe's primary forges for these precious metals. Other anomalous grains tell different, equally dramatic stories. A specific overabundance of certain isotopes might be the unique signature of a particular type of supernova, one that exploded in just the right way to create a chemical recipe we have never witnessed before. Another grain could have been born in the powerful, dusty winds of a rare class of star, like a Wolf-Rayet star, which sheds its outer layers in a furious stellar hurricane laced with unusual elements. Each time a new anomalous grain is identified, it forces astrophysicists to go back to the drawing board. They must re-evaluate and refine their complex models of stellar nucleosynthesis, the very rules that govern how stars build the elements of the periodic table. What does it mean if our models cannot account for this tiny speck? What rare process, what forgotten type of stellar death are we only now discovering through its atomic legacy? This makes the hunt for these outliers far more than a niche pursuit. It is a fundamental scientific process. These rare grains are the crucial clues that poke and prod at the edges of our understanding, compelling us to redraw the map of cosmic element production. With every anomalous grain discovered, a new, previously hidden chapter of the universe's violent and creative history is reluctantly revealed. The same instruments that can read the atomic song of a single stardust grain are now whispering secrets here on Earth. To study the universe's most ancient materials, scientists had to invent tools of breathtaking sensitivity. These devices, born in cosmic laboratories, have quietly revolutionized fields far beyond astronomy. Consider the mass spectrometer, a machine that weighs atoms. The versions developed to analyze the isotopic barcodes of Presolar grains are so precise they can detect a single unique atom among billions of others. This incredible sensitivity is a powerful new sense for our planet. Environmental scientists now use these advanced spectrometers to trace the faintest contaminants in water supplies, tracking a specific pollutant back to its exact industrial source with the same certainty that astronomers trace a dust grain to its parent star. In geology, they can date rock formations with unprecedented accuracy, reading Earth's own deep history written in the subtle atomic ratios of its minerals. The technology has even entered the world of forensic science, where analyzing the unique isotopic signature of a hair, a fiber, or a speck of soil can place a suspect at a specific location, solving terrestrial mysteries with a technique forged to decipher cosmic ones. The pursuit of Stardust did not just give us a new way to look at the sky, it gave us a new lens to examine our own world. This technological transfer extends to the very materials that make up the dust grains themselves. Under electron microscopes, researchers discovered that stardust possesses incredibly resilient and complex nanostructures, architectures built by nature under extreme conditions. Materials scientists study these tiny blueprints to inspire the creation of new, stronger, and lighter nanomaterials. The layered, onion-like structure of some carbon grains, for instance, informs the design of better lubricants and more durable protective coatings for everything from electronics to jet engines. We are learning how to build from the universe's own recipe book, reverse engineering the durable designs of cosmic dust to improve our own technology. Even the challenge of catching dust without destroying it led to profound innovations. The aerogel used in the Stardust mission, a substance so ethereal it is called frozen smoke, was developed specifically to softly capture hypervelocity particles. The knowledge gained from how these particles interact with such exotic materials has direct applications in spacecraft shielding, helping engineers design better protection for satellites and astronauts from the constant, high-speed rain of micrometeoroids. This same physics is critical for the emerging field of planetary defense, where understanding the precise effects of a high-energy impact is essential for any strategy to deflect a threatening asteroid. The connection is profound. The relentless human drive to answer a fundamental question, to touch a piece of a star, did not just expand our knowledge of the cosmos. It forced us to become better engineers, more perceptive chemists, and more precise detectives of our own planet. The quest to understand our cosmic ancestry consistently spins off a quieter, more tangible legacy, one that builds a safer, healthier, and more technologically advanced world right here at home. This scientific truth moves beyond a simple fact and into the realm of profound philosophy. We are not just living on a planet, we are the temporary arrangement of ancient cosmic materials. Every thought you have is a conversation between atoms born in stellar explosions. Every feeling you experience is powered by chemical reactions fueled by stellar debris. This is not a metaphor, it is a physical, verifiable reality. That iron in your blood did not originate on Earth, it was forged in the final moments of a dying star billions of years ago. The calcium that scaffolds your bones was once part of the swirling dust cloud that collapsed to form our solar system. This knowledge shatters the illusion of separation between us and the void above. It builds a tangible bridge between the human scale and the galactic, connecting the microscopic world of our cells directly to the life cycles of stars. This shift in viewpoint, often called the cosmic perspective, carries a powerful emotional resonance. It can evoke a deep sense of belonging to a story far grander than any single human life. We are not isolated beings on a lonely rock. We are participants in an epic narrative of cosmic recycling that has been unfolding for over 13 billion years. This realization naturally encourages a certain humility. It challenges the ancient, human-centered notion that we are the pinnacle of creation, separate from and above the natural world. Instead, we are a beautiful, conscious expression of the universe itself, one of its countless temporary creations. Our planet is a single, tiny stage in an immense cosmic theater. Yet, this humility does not diminish our significance, it redefines it. The same processes that scattered dust across the galaxy also arranged that dust into a form that can look back, wonder, and seek to understand its own origins. In a very real sense, we are the universe awakening. We are a mechanism for the cosmos to become aware of its own beauty, its own history, and its own staggering complexity. The dust has not just formed us, it has begun to think about itself. The search for cosmic dust has escaped the confines of elite laboratories and landed squarely in our living rooms. Anyone with a computer and a curious mind can now join the hunt through citizen science projects like NASA's Stardust at Home. This initiative presented volunteers with a monumental task to scan millions of microscopic images of the aerogel collector that captured particles from a comet's tail. Their mission was to find the tiny, carrot-shaped tracks left by potential interstellar dust grains, impacts so subtle and unique that even sophisticated algorithms struggled to identify them reliably. This is where the human brain, with its unparalleled talent for pattern recognition, becomes an indispensable scientific instrument. Thousands of everyday people, from students to retirees, devoted their time to this meticulous cosmic treasure hunt, their collective attention sifting through a digital haystack for the tiniest of needles. Each potential track flagged by a volunteer was a candidate for further professional analysis, a crucial first step in the discovery process. This collaborative model does more than just process data. It forges a powerful, personal connection to the scientific endeavor. When you are the one who identifies a track that leads to the confirmation of a genuine interstellar particle, you are no longer just a passive observer. You become a direct participant in the story, a co-discoverer of a speck of stardust that has traveled for millions of years to tell its tale. This profound engagement transforms abstract space science into a tangible, human pursuit. It demonstrates that the frontier of knowledge is not a distant place reserved for a select few, but an open field where collective curiosity can yield real, groundbreaking results. By democratizing access to discovery, these projects build a deeper and more widespread appreciation for scientific research, cultivating a global community of supporters and inspiring future generations to look up at the stars and see a universe they can actively help explore. The next leap in cosmic forensics is already taking shape on drawing boards and in laboratories around the world. We are moving beyond the chance encounters of meteorites and the brief snapshots of comet flybys. The future demands a dedicated hunt, a series of missions designed with one primary goal: to capture a wider, more pristine library of stardust. One of the most ambitious proposals involves sending a spacecraft on a fast trajectory out of our solar system, beyond the heliosphere. This is the vast bubble of particles and magnetic fields blown out by the sun, a protective cocoon that also filters and alters the dust flowing in from the true interstellar medium. A probe venturing beyond this boundary would be like a diver finally reaching a pristine ocean current, able to collect interstellar dust grains that have never been touched or modified by our sun's influence. These would be the most authentic samples of the galactic environment ever gathered, a direct taste of the raw material drifting between the stars. Another concept seeks to use the moon itself as a giant, natural collection platform. Imagine deploying vast, ultra-clean panels on the lunar surface, sheets of a specially designed material left exposed for years. In the airless silence of the moon, these panels would slowly accumulate a rain of cosmic dust without any of the contamination from Earth's atmosphere or pollution. A single square meter left for a decade could harvest thousands of microscopic particles, building a statistical treasure trove that would allow scientists to understand the true diversity of dust types visiting our cosmic neighborhood. Back in the lab, the tools to read these grains are becoming almost unbelievably sensitive. The next generation of ion probes will be able to measure the isotopic composition of a sample 1,000 times smaller than what we can analyze today. This means that a single microscopic grain, once just a data point, could be subdivided and analyzed layer by layer, revealing a detailed timeline of its formation as it grew in the stellar wind of its parent star. With these advances, we are not just hoping to find more stardust, we are preparing to read its story in high definition. The coming decade promises to transform our understanding from a collection of fascinating anecdotes into a full demographic census of the cosmos. We will move from knowing a handful of stellar genealogies to possessing a rich family album, detailing the lives and deaths of countless stars whose legacy now drifts silently through our celestial backyard. This microscopic thread of dust weaves together the entire cosmic tapestry. The death of a star in a distant galaxy is not an isolated tragedy. It is a necessary event that directly enables the birth of a planet in another. The complex chemistry simmering on the surface of a single dust grain in a dark nebula is a prerequisite for the biochemistry that would one day pulse through a living cell. Your own physical existence is a direct consequence of this chain, linking galactic evolution to the air in your lungs. This is the profound interconnectedness that cosmic dust reveals, forcing us to see the universe not as a collection of separate objects, but as a single, breathing, integrated system. To truly understand a single speck, you need the mind of a stellar physicist to know how it was forged, the insight of a galactic astronomer to trace its journey, and the skills of a chemist to decode its atomic message. There are no bystanders in this cosmic story. The violent death of one massive star by seeding its neighborhood with dust rich in heavy elements can determine the composition and potential habitability of thousands of future worlds that form from that enriched material. Its actions create a legacy that ripples across light years and billions of years, influencing events far removed from its own brief, brilliant life. This perspective transforms our approach to knowledge itself. It encourages a unified science where the smallest detail, a single anomalous isotopic ratio in a grain smaller than a bacterium, can illuminate grand patterns of galactic birth and death. The universe whispers its secrets not in grand pronouncements, but in the silent, resilient language of dust, a language that connects everything to everything else. This profound connection to the cosmos is not merely a scientific fact, it is a call to action. Realizing that we are made from ancient stardust and share a universal ancestry with every living thing on our planet fundamentally reshapes our sense of responsibility. It dissolves the artificial barriers we have constructed between nations, species, and ecosystems, revealing a deeper, shared lineage written in atoms. This cosmic perspective fosters a powerful sense of planetary stewardship. Our world is not just a random rock, it is an incredibly rare and precious oasis. The same intricate chain of stellar events that delivered the iron for our blood and the carbon for our cells also crafted a delicate, self-regulating biosphere that exists within a vast and overwhelmingly inhospitable universe. Understanding its rarity underscores its fragility and its immense value. This knowledge argues powerfully for its preservation, transforming environmental care from a political issue into a universal human imperative, a duty to safeguard a singular cosmic inheritance. Looking even further ahead as our technology advances, we must also contemplate the ethics of our future role in the cosmic cycle. One day, humanity may develop the capability for astroengineering, perhaps learning to manipulate matter on a grand scale or even influence the formation of new stars and planets. With such power comes a profound ethical question. Do we have the right to alter the very processes that created us? Intervening in the natural cycles of stellar death and rebirth is a responsibility of almost unimaginable scope. It forces us to consider whether we would be wise stewards of the galaxy or reckless inheritors, potentially disrupting billion-year-old rhythms for short-term gain. The pursuit of this knowledge is therefore far more than an intellectual exercise. It is a journey that actively shapes our worldview, our values, and our collective conscience. It teaches us humility by revealing our minute place in space and time, while simultaneously granting us a majestic role as the universe's conscious witnesses. This cosmic perspective does not provide easy answers, but it offers a crucial framework, a starlit guide for navigating our future with wisdom, compassion, and a deep respect for the intricate web of existence that binds us all. But this profound scientific truth has a cultural shadow. The poetic idea of stardust has been embraced by popular culture, sometimes twisting into pseudoscientific claims that obscure its real wonder. You might encounter products or practices promising miraculous benefits from consuming or being exposed to what they call stardust, suggesting it carries some mystical energy or healing power. This is a fundamental misunderstanding of its nature. A grain of cosmic dust is a physical, mineralogical object. It is not a magical powder. Its power lies in its tangible chemistry, the iron that carries oxygen in your blood and the carbon that forms your DNA, not in any unproven spiritual energy. This chemical reality is, in its own way, far more staggering than any fantasy. Another common misrepresentation surfaces in some modern interpretations of astrology, where cosmic dust is sometimes granted an undue influence over daily human events and personalities. While the planets and stars are real physical bodies, attributing our personal fortunes to the dust between them conflates poetic metaphor with causal mechanism. The true influence of stardust is not in dictating your destiny, but in having literally built your body from the ground up over billions of years. By drawing this clear line between the rigorous, evidence-based field of astrophysics and these unfounded claims, we do not diminish the awe. We refine it, replacing mysticism with a genuine understanding of nucleosynthesis and galactic recycling allows for a more authentic and ultimately more meaningful appreciation of our place in the cosmos. Knowing the real journey these atoms have taken from stellar cores to the palm of your hand fosters a connection rooted in the verifiable grandeur of the universe, a story incredible enough on its own without requiring any invented magic. Even with our most powerful tools, the full story of cosmic dust remains frustratingly incomplete. We have mapped its journey and decoded its atomic language, yet fundamental gaps in our knowledge persist. One of the biggest puzzles lies at the very beginning, in the chaotic aftermath of a stellar explosion. We know dust forms in supernova, but how much and how efficiently remains a heated debate. The precise conditions within that expanding fireball, the exact cocktail of elements and the rate of cooling, all dictate how many solid grains can nucleate and survive. For some types of supernova, our models predict a veritable sandstorm of new dust, yet our observations sometimes show far less. This suggests that much of the freshly forged dust might be destroyed almost immediately, crushed in the very same shockwaves that gave it life. We are still learning the delicate balance between creation and destruction in these cosmic forges. The destructive forces within the interstellar medium itself are also poorly measured. We know cosmic rays and shockwaves erode dust, but we lack a precise census of this slow, grinding decay. How many grains are shattered over a million-year journey? How many are simply worn away, atom by atom, back into the gaseous state from which they came? Quantifying this universal wear and tear is crucial for understanding the true lifespan of these cosmic time capsules. And while we have observed dust being blown out of galaxies, we struggle to put a number on this great exodus. What percentage of a galaxy's dusty legacy is permanently lost to the intergalactic void, and what fraction eventually rains back down to fuel new generations of stars? This galactic accounting is key to modeling how galaxies evolve from dusty, star-forming spirals into quiet, dust-poor ellipticals over billions of years. The most profound mystery, however, concerns the very first dust of all. Our entire narrative rests on the existence of population 3 stars, the mythical first generation of colossal, pure hydrogen and helium giants. Theory states that their supernova must have seeded the infant universe with the first heavy elements and the very first dust grains. These primordial specks would have been the seeds for everything that followed, the dust that started the entire cycle. Yet, despite searching for their unique isotopic signature, we have never conclusively identified a single grain from a population 3 star. They remain ghosts, the hypothetical ancestors in our cosmic family tree. Finding one would be the ultimate prize, a direct sample from the dawn of time. These unanswered questions are not failures, they are the very engine of modern astrophysics. Every unknown is a destination for a new telescope, a target for a more sensitive instrument. The fact that we can so clearly define what we do not know is a testament to how far we have come. It means the map of our ignorance is now detailed enough to guide the next great voyages of discovery, pushing us to look deeper and think more creatively about the silent, dusty carriers of stellar DNA. Our journey through the cosmos reveals a story written in dust, a narrative of breathtaking beauty and profound connection. We have traced the path of intergalactic dust from the fiery hearts of dying stars to the delicate grains drifting between galaxies, each one a vessel carrying the elemental DNA that builds worlds and sparks life. This is not a distant legend, it is our own origin story. We have witnessed how the tools of science allow us to decode these cosmic messages, translating the silent atomic language of a grain into the life history of a star. This knowledge fundamentally transforms our perspective. We are not just observers peering out at a foreign universe from a lonely rock. We are an active, living part of its grand, ongoing narrative. The iron in your blood, the calcium in your bones, the very air you breathe, all of it is recycled stardust, temporarily assembled into a form that can look back at the sky and understand. So the next time you gaze up at the night sky, see it not as a distant, cold void, but as an extended home filled with the luminous remnants of our stellar ancestors. Let this understanding ignite a lasting curiosity and wonder within you. What does this cosmic connection mean to you? Share your thoughts in the comments below, and if you want to continue exploring the mysteries of space, be sure to subscribe for our next journey together.